So let me explain. Yeah. So this is a important part. So we need to, after this step, then everything is easier. Yeah. Okay, all right. Yeah. So now, first let me explain what we are doing here. Yeah. Oh, Michelle, roughly, yeah, so let me look at the chat message. Roughly when you will have midterm part B grade. Yeah, I'm doing that. All right, Michelle. Yeah, let me tell you, right now I'm halfway, okay? So your class, you have total 15 students. So now I'm working on number 7, okay? Yeah, about halfway. So I estimate I can pretty much complete it late tonight and early tomorrow morning, all right? Yeah. So tomorrow morning, so it is very likely you can see your grades posted, right? Yeah, so, yeah. Yeah, so halfway, yeah. Good, all right, yeah. Any question, just let me know. Yeah, no problem. Yeah. All right, so what we are doing here, we want to find the worst case efficiency for the binary search. Yeah. So last time I said, although this question looks pretty easy, yeah, why we spend so much time? Yeah. The reason is, most people, if you ask this question, the worst case efficiency, then those people usually, based on their impression or intuition, so they will give you a close formula. So the formula, approximate formula, very close to the final answer, but not exact. All right? Yeah, let me remind you. So last time I said like this. Yeah. So the closed form, yeah, because the binary search, how many comparisons for the worst case? Yeah. So then, based on your intuition, most people write this formula. Log base 2 of n, right? Yeah. But this function, most of the time, it does not return an integer number, right? Most of the time, it does not return an integer number. So then, in order to get an integer number, so then people modify slightly to get an integer number. One way is the floor function, and another way is ceiling function. Yeah. Okay, 2 possible ways people use can easily convert it to an integer expression. Yeah. But these 2 expressions, none of them gives us an accurate formula. Yeah. So not exact, okay? Slightly different. Yeah. So the exact one, if you use the first expression, you need to add a 1 to be exact. For the second version, yeah, because ceiling function, so you make the ceiling function, but you need to plus 1 inside the parenthesis, like that, right? Yeah. So that's the exact formula, all right? And here, I'm deriving that formula, okay? Yeah. So I explain how to get these 2 formulas. Yeah. All right. Yeah. Then we have this inequality first. Yeah. Yeah. How did we get this inequality? Remember, we used the problem size reduction understanding. For the binary search, every time we drop half of the data, right? So we apply the elimination method. When we compare the given key to the median of the array, median of the array, when we do that comparison, we can drop 1/2. So no matter what the result it is, you can drop approximately 1/2 of the data. But when you drop, eventually you need to stop, right? Yeah. So last time we analyzed, so we found the criteria. Yeah. We find criteria telling us when to stop. Yeah. So there, from that criteria, yeah, upper bound, lower bound, there we get this inequality. Okay? Yeah, we get this quality. Now let's continue from this inequality. Yeah, yeah, but when you look at this inequality, all right, Shaza, join us. Yeah. All right. You can see left hand, so this inequality, actually we have two inequalities, right? Yeah. Left half and the right half. The left half inequality, we include the equal case included. But the right half, we do not include the equal case, right? Yeah. So we do not include the equal case. Yeah. So that means, you know, this inequality is not very tight. We want to tighten it, you know, make it sharper. Yeah. So we can improve it. Yeah. We can improve it a little bit. Yeah. Because if the right-hand side part, right half of the inequality does not contain the equal case, that means there is a gap, right? There is a small gap. Okay, yeah. So when we can find an equivalent inequality containing the equal case, that's the best we can get. Okay, the best we can get. Yeah. So because here we want to get the best description, you know, or let me say the best constraint between n and k. Yeah. Yeah. So this inequality, it is a constraint between k and n, but it's not the best. We have a little room to improve it. All right. So here, let me show you that step, the little step. All right. All right. Here, we know all of them are integers, right? Yeah. All the expressions in this inequality are integers. All right. Then let's look at the, we can view this inequality in a special way. Yeah. So you can see actually this inequality provides us the lower bound and upper bound for n, right? Yeah. So lower bound and upper bound. Yeah. Lower bound is this one, the upper bound, right? Yeah. All right. So now let's view this inequality in this special way. I want to get the range of n. Range of n. Okay? Yeah. Yeah. All right. Range of n. If k is known. Yeah. So here we assume k is known. Yeah. Yeah. If k is known, yeah, then what is the lower bound for n? Yeah, that's obvious, right? Yeah, that's obvious. Yeah. This time, this equal case is important. Okay? Yeah. Yeah, because n could be equal to 2 to the k minus 1, then that 2 to the k minus 1, that's the lower bound. Yeah. All right, so we write 2 to the k minus 1, the lower bound. Then the next question, what is the upper bound of n? Or I should say in a better way, what is the smallest upper bound? Yeah, because sometimes people argue, if you say just upper bound, you do not say smaller upper bound. We can write 2 to the n. It is upper bound, right? It is greater than n, obviously. Yeah. So you can put a very large expression. So here, actually, what we want to have is the smallest upper bound. That's more useful. Okay? So we are more interested to get the smallest upper bound here. All right. Now, I ask this question. Yeah. But this time you need to pay attention to this, unequal sign. It does not contain the equal case, the unequal part. Yeah. So what is the smallest upper bound for n? Yeah. Definitely not this one, right? Yeah, because n can never be equal to 2 to the k, right? Yeah. So it's not the smallest. It is not smallest upper bound, because you cannot take the value of n to be 2 to the k. So you cannot use it as the upper bound. Yeah. So what you can use? Well, the integer number should be smaller than 2 to the k. So that is 2 to the k minus 1. So this is the upper bound. All right? Minus 1. Yeah. Minus 1. That's the upper bound. Yeah. Then, yeah. So after you get the largest lower bound and the smallest upper bound, yeah. So this time you get the best range description for n. Range description. Yeah. So now both sides containing the equal case. Equal case. All right? Yeah. So after we get over this step, then the remaining part, obvious. Yeah. Very obvious. All right? So so you have this. Okay? Yeah. This time containing equal sign. Yeah. N plus 1 less than or equal to 2 to the k. Yeah. All right. Then, yeah, we take log of base 2. Yeah. Yeah. All right. So we rewrite it, take log of base 2, that you have, both sides, you have the equal case. Yeah. Equal case. Yeah. Because the reason we write this way, yeah, we need to go back to our original understanding of the binary search. In our binary search, n is given, right? N is known. The size of the array, n, is known. Yeah. And k is unknown. We need to calculate, we need to estimate that k. So we need to represent k in terms of n. Yeah. Yeah. All right. So for that's the reason we write in this form. Okay? Here you can see actually we write the range for this k. We write the range for this k. Okay? Yeah. Yeah. So what is this k? Okay, let me remind you again. The k corresponding to number of comparisons for the worst case. That is the k. Okay? Yeah. Number of comparisons for the worst case. All right? Yeah. All right. Then the last step. The last step. All right. Log of base 2 the two expressions related to the log base 2 of n, they are not integer expressions, right? They are not integer expressions. So we need to convert these two expressions to integer expressions by taking floor function or ceiling function. Floor function or ceiling function. All right? Yeah. So that last step. Yeah. In that step, yeah, left-hand side, yeah, less than or equal to k. Yeah. Now, when we use an integer expression, we want to use the ceiling function. Okay? Yeah. Yeah. Because this expression less than or equal to k, k is an integer, then its ceiling function also less than or equal to k. Right? Yeah. Yeah. So we use the ceiling function at the left-hand side. Right-hand side, we use floor function. Yeah. Yeah. Floor function, because if it is not an integer, then we take the floor function, it becomes integer, it should be greater or equal to k. Yeah? K is an integer. So when we take the floor function of that expression, it is also greater or equal to k. Right? Yeah? So we left-hand side, we do the ceiling function. Right-hand side, we do the floor function. So after that step, then we have two formulas. Left-hand side formula, right-hand side formula. Two formulas. Okay? All right. From the left-hand side formula, k sub max, here I use this notation represent the maximum number of comparisons you need. So that means the worst case, right? Yeah, because for the worst case, you need a maximum number of comparisons in the binary search. So that number, the left-hand side expression is ceiling function of log base 2 of n plus 1. Yeah. Right-hand side expression, 1 plus floor function of log base 2 of n. Yeah. Yeah. All right. Yeah. But there is, the final step after you get these two versions. Yeah, these two versions formula quite different, right? Yeah. Their looks quite different. Yeah. How do you know they both correct? Okay, right? Yeah. So actually these two expressions, they are exactly the same. Exactly the same. Okay? Yeah. But it is not easy to see why they are the same. Yeah. Why they are the same. Yeah. Yeah. In our textbook appendix, we have some basic formulas. Yeah. So this one is one of the basic formulas given in the appendix of our textbook. Yeah. But we can also prove it. Yeah. If any of you want to prove it, we can prove it. But if you want to prove it, we need to use mathematical induction. Okay, mathematical induction. Yeah. But here I don't want to use I don't want to prove it at this point. Yeah. I want to save some time. Yeah. Yeah. Because I need at least 20 minutes to prove it. Yeah. All right. So I skip it. Yeah. All right. Yeah. So then we have the formula. Okay? Yeah. After this step, we have the formula. Now discussion. The best case, one comparison, right? Yeah. So the best case, one comparison. Because when you compare the given key with the media of the array, you get it. They are equal. Yeah? They are equal. One comparison. You find it. Yeah. So that's the best case. Only one comparison. Yeah. The worst case, yeah, this is the worst case. All right. Then next question I also want to ask you, yeah, after best case, worst case, we also need to look at the average case. Yeah. The average case, here, let me ask you, if we want to calculate the average case, do you feel, so there, sometimes people may like to use the, basic understanding of the average case formula, just, take average directly, 1 plus that worst case expression, then divided by 2. Do you think we can use this way to calculate the average case? Yeah. Here the answer is no, you cannot do it. You cannot do this way. It's incorrect. It is incorrect. Okay. Yeah, let me explain. So why it is incorrect? Yeah. I remember in our discussion before, some previous lecture, I talked about the average case. Yeah. Where all of your cases are distributed linearly, then you can use this way to calculate average. Yeah. But for the binary search, then all the cases are not distributed linearly. So what means linearly? Okay, yeah, linearly here. If I use a simple diagram, it's like this. Suppose you have the best case. Best case, I use the height of this line segment. Worst case, this much. Okay, the best case, worst case. Then all the other cases between best case and worst case, they are distributed along the line, straight line between. Yeah. So that we call it, all other cases distributed linearly. Okay? Yeah. But for our binary search, it's not like that. Okay? For the binary search, the distribution is like, it's a curve. Okay? Yeah. In that case, so then you cannot take the, you cannot take average case, like that. You cannot, right? Yeah. All right. So the average case, if I use diagram to show what's the average case, yeah. So if in this, curve situation, what is the average case? Yeah. The average case should be you draw a rectangle. The area of this rectangle should be the same as the area of that, curve part under the curve, the area under the curve. This height is the average case. That height is the average case. Right? Yeah. All right. So here you can see calculating the average case. You need to do more work. Okay. More work. All right. Yeah. Yeah. But in order to help you understand how to calculate the average case, now, because in your homework assignment number 2, you will have one question. You need to calculate the average case efficiency. Yeah. So here, let me use one example. Yeah. This example, we only do a simple, relatively simple case. N equals 7. Yeah. For n equals 7, this time the binary search. Yeah, we need to draw a binary tree corresponding to the binary search steps. Yeah. That binary tree will be a complete binary tree. Complete binary tree. So all the levels are full. Complete binary tree. Yeah. That's a relatively easy situation. Yeah. All right. So the next B.3, let me show you how to find the average case efficiency of the binary search. But we only do a special example, n equals 7. Okay? All right. So then in your homework assignment, then you will do a relatively harder one. So n equals 20 something. Yeah, n equals 20 something. Yeah. All right. Here, we need to, use a diagram to show the comparison information in a binary tree. Yeah. All right. Our data, it is a 7-element sorted array. Yeah. We use this line segment. Then a given key. We need to do comparison. The first time, so here you can see, yeah, compare it with the median. Yeah. Then if it's smaller than that, second comparison, then third comparison, right? Yeah, third comparison. Yeah, but here we like to use a binary tree to, show the structure of all these comparisons in different levels. Yeah. So then we can see better. Yeah. All right. Yeah. Yeah. Here I put a assumption. Assume V is in the array. Yeah, because there is a possibility V may not be in the array, right? Yeah. If V is not in the array, then you have the worst case, right? Yeah, because all your comparisons will fail. Yeah. All your comparisons will fail. Yeah, so that's the worst case. Yeah. So that's easy. Yeah. So we know the answer. That's easy. Yeah. All right. So now we want to, look at all the cases. May not be the worst case. Yeah, all other cases. Yeah, worst case. We already have the formula. So we don't worry about the worst case. We already have the formula. So we want to see other cases. Yeah. So for that reason, we make this assumption. Okay, all right. Then, but for the general discussion, because general discussion, you cannot make that assumption, right? Yeah. So for the general discussion, then you need to have some probability number, P. Yeah, just like our linear search. Yeah. Our linear search, we assume some probability P. Yeah. All right. Yeah, but here we, our focus is not on that part. So our focus is on, all the cases you have in the binary search. Yeah. When V is in the array. Yeah. When the V value, you can find it in the array. Yeah. All right. Then the root of the binary search, node number 4, should be the root. Yeah. Because the first comparison, we compare V with element root node number 4. Yeah. So we put it at the root of the binary tree. Then we have 2 branches. Yeah. So for this, in order to get a match at the root, we need 1 comparison. Here my 1 means 1 comparison. You hit that root node. Yeah. All right. Then there are 2 possibilities. So we go left branch and the right branch. Yeah. For the left branch, we have a left subtree. Yeah. Left subtree of this binary tree. Then the next comparison in the left subtree, node number 2. Okay. The next comparison in the right subtree, that's the node number 6. Okay. So that's the, next level. Yeah. And in this level, in order to get a hit in this level, we need 2 comparisons. 2 comparisons. Okay. All right. So then another level going down. Yeah. All right. So node 1, node 3. Okay. Yeah. So two left child nodes of the node number 2. Yeah. Similarly, yeah, the two child nodes of node number 6. Yeah. And number comparisons for this level, 3 comparisons. Yeah. So this simple binary tree gives us all the information about all the comparison cases for this binary search. Okay? Total 7 nodes. Yeah. So you can find all the comparison number for these 7 nodes. Okay? All right? Yeah. Now we are ready to calculate average case efficiency. Yeah. So when we calculate the average case efficiency, then we need to use the structure of this binary tree. All right. So let me write the final formula. All right. All right. Average number, the denominator easy, total number of cases 7. Okay. Now, the numerator then, yeah. So we look at the number. Yeah. The first term 1 times 1. The first one means number of comparisons. Okay. Yeah. So in this level, okay, number of comparisons. Okay. And the second operand meaning is the number of nodes in this level. Okay, all right. So, yeah, then the first term, because number of comparisons, 1 comparison. Number of nodes, only 1 in this level, right? So that's why 1 times 1. Yeah. Then the second term, the number of comparisons, 2, and how many nodes in this level? 1, 2. There are a node number 2 and a node number 6. Only 2 nodes. That's why 2 times 2. And the third term, the number of comparisons, 3, and how many nodes in this level? There are 4 nodes. That's why 3 times 4. Okay? Yeah. Then you add them together, so you get the final answer, 17/7. Yeah. It's not an integer. Okay? It's not an integer. Yeah. Average case. Yeah. So when you calculate the average case efficiency, we know in general case, the answer should not be an integer. The average, when you take the average, usually you do not get an integer answer. Yeah. The reason I say this is because some students I noticed, yeah, after they find the answer of the average case efficiency, then they convert it to integer. Then they round it up or round it down to give me an integer answer. The reason they do that is because they feel this number represents the number of comparisons, right? When you talk about the number of comparisons, they feel, here I say they feel, they should use integer numbers. Yeah. That's true for best case and the worst case, but not true for average case. Average case, because after you take the average, how can you get an integer number? In general, you cannot get integer number. And don't do round it up or round it down. Okay? Yeah. When I ask you in the question, I want you to give me precise number. Okay? Accurate number, not approximate number. Okay? So your fractional answer is good. Okay? Don't do rounding up or down. All right? Yeah. No rounding operation. Okay? Yeah. just give me the fraction answer. Yeah. All right. So we complete that topic. Okay. All right.
Yeah. I have a question.
Okay. Yeah. What question?
For that average case, is there a N formula for it?
Oh yeah. Okay. Yes.
Like
Yeah.
massive?
Right. Yeah. Actually, yeah. Good question. Yeah. There is. Yeah. There is a formula. Yeah. But the formula pretty complicated. So the formula people derive like this. First, they assume, because the formula is easier for the complete. So easier for n equals 2 to the k minus 1. Yeah. Because this corresponds to the, complete binary tree. Complete binary tree. So there is a formula for this case. Yeah. But for the general case, for the general case, then, because the situation relatively complicated, so then people use estimate, approximate formula. Approximate formula. You can find it. So you can find it on web. I saw that before. But when we do the calculation, because I understand you asked this question. Because then when I give you this question in homework assignment or final exam, then you just plug in, you apply the formula, right? Yeah. But that formula, in general, it's an approximate formula. Okay? It's not a precise formula. It's an approximate formula. So if you do that, you get approximate answer. So not, And another thing is, that formula is for the average case for all the nodes in your binary tree. But in our homework assignment number 2, I ask you for average case for some of the nodes, not all the nodes. All right. Suppose you have all the nodes here. Suppose this is all the nodes you have. Then, in my condition, I exclude some of the nodes at the left end. I exclude some of the nodes at the right end, and I only ask you to give me the average case efficiency of this remaining middle part. In that case, you cannot apply any formula, right? So you have to use our current way. So what we just did in this example to do the calculation. Okay? So but the answer is there is approximate formula, not exact formula. But even the approximate formula, that's for the whole binary tree, not the partial binary tree. Okay? Average case is for the whole binary tree, not partial. But in our questions, one in the homework assignment number 2, and another one probably in final. But final, I may not include that question. So if you do well in the homework assignments, then in the final, I will not give you that question again. All right. So that's this topic. Then the last topic for part B, selection problem, the general selection problem. Here for this general selection problem, I like to give you the final result. So I do not want to talk about the algorithm finding solution of the general selection problem. Yeah, because that's very complicated. Yeah, that algorithm is given in our textbook. Yeah, but if I talk about that algorithm, then we don't have enough time. Yeah, so here I just give you the final result. Yeah, all right. The general selection problem, yeah, given an array and a positive integer k. Yeah, here this k representing the rank number. Okay, yeah. All right. The question: how to find the kth smallest element? Yeah, that's a general. When k equals 1, then the smallest element. When k equals n, then the largest element. Yeah. So then you have, k equals 2, 3, any number in the middle. Yeah. Yeah. So, yeah. Some people call it order statistic. Yeah. Kth order statistic. Yeah. But, it is rarely used. Yeah. Yeah. More general, people use a rank number. A rank equals this k. Yeah. All right. Yeah. Analysis. Yeah. The data is unordered. Otherwise, if the data is ordered, then it's trivial, right? Yeah. So you don't need any comparison. You just go to the, location. Yeah. The kth location, so you can find it. Yeah. So we assume the data is unordered. Yeah. But another question. Yeah. Some people may feel to solve this problem, we can sort the array first. After we sort it, then you can find the kth smallest element easily, right? Yeah, yeah, yeah. But here there is a problem. Yeah. When you sort the array, how much work do you need to do? Think about that. How much work you need to do? Yeah. Too much work. Too much work. Yeah. Sorting. Yeah. Sorting. Yeah. If I use the asymptotic notation, generally when you do sorting, you need to use n log n. You need to do this much work. That's too much. Yeah. So without sorting, if you want to find the kth smallest element, without sorting, you can do better than this, because you don't have to. You don't have to sort the array. Yeah, you overdo it. You overdo it. Okay. Yeah, yeah. So that's the problem. All right. Yeah, yeah. Then, yeah. So here, let me just describe the solution a little bit. Yeah, describe solution. Yeah. So I don't want to go through all the details, but give you some high-level explanation. Yeah. Divide and conquer. Yeah. To solve this problem, we need to apply the divide and conquer approach. Yeah. So, how to divide the problem? Yeah. Divide into two subarrays. So when we divide the given array into two subarrays, remember we apply the elimination method here. Yeah. And after certain number of comparisons, we need to drop one of the two subarrays. Yeah. Similar to the binary search, but it is more complicated than the binary search. Binary search divide step very easy, right? After one comparison, then you can drop one of the two subarrays. Yeah. But this one, you need to do a lot of work to divide the given array into two subarrays. Then you can drop one of the two. Okay? Yeah. All right. Yeah. Then you do recursion. Yeah. Because after you drop one of the two, then you apply recursion on the remaining subarray. You do the same process. Yeah. Divide and conquer, drop. Yeah. but much more complicated than a binary search. Yeah. All right. Yeah. And also, yeah, so for the detail, because this number, you need to use this number to help you figure out those two subarrays. Yeah. Determine how to divide the given array into two subarrays. Yeah. All right. Yeah. Elimination idea. Yeah. So here, let me use a simple diagram to describe the elimination idea. Yeah. All right. Here, one high level. Yeah. Here, I want to remind you. I talked about one principle before. Yeah. I talked about when we make a decision on our data in order to avoid worst case efficiency, bad worst case efficiency. Yeah. Here, let me mention that principle again. So I call the balancing principle before. Okay. Yeah. Balancing principle. Okay. All right. So when we need to make a decision to divide the data, we want to avoid extremal cases. Avoid extremal cases. Okay? So what's the extremal cases? Suppose this is your whole data. Okay? So when you do divide and conquer, when you do split, if your split is very close to one of the two ends, left end, or your split very close to the right end, then that's the extremal cases. Okay? Yeah. Extremal cases. Yeah. Yeah. Because that's the most unbalanced division. So you want to avoid those unbalanced divisions. So you want to restrict your division somewhere in the middle. Okay? Yeah. Avoid those, extremal cases. Then you can avoid poor worst case efficiency. Yeah. Poor worst case efficiency. That's the basic idea here. All right. All right. So the two cases, one case elimination from the left end, another elimination from the right end. Yeah. All right. So here I use the diagram here. Yeah. Because these two are pretty much symmetric. So we only need to look at one of the two cases. Yeah. All right. And so for that algorithm, in order to avoid bad worst case situation, yeah, when you do the division, you need to do a lot of work to help you eliminate the cases that is close to the left extremal cases or the cases that is close to the right extremal cases. So you avoid those two extremal cases. Yeah. Then you do divide and conquer only somewhere in the middle. Okay? Somewhere in the middle. Yeah. So that, if you look at the details of the algorithm given in our textbook, yeah. So this part is 30% of the data. Okay? This part, another 30% of the data. Okay. Yeah. So you divide. So your divide point is somewhere between. Okay? Left 30%, right 30%. Yeah. So now you can see in this way you can avoid poor worst case situation. Yeah. All right. Then the final result. Yeah. The final result, if you do this way, divide and conquer, recursion, at the end, you get an algorithm that is big theta of n. Now you can see, you compare big theta of n, and if you sort it, you need to do big theta of n log n. That means you can do better. Yeah, yeah. So that's, we call this algorithm, we call it a linear algorithm. Because this is a linear function, okay? Linear algorithm. So we have the solution to the general selection problem, we have this linear algorithm. That's the result. Okay, all right, yeah, yeah. So that's what I want to talk about that general selection problem. Yeah. So just let you know you have that information. Okay. Yeah. So what you can do? Yeah. The detail of the algorithm, you can find in our textbook. Yeah. All right. Yeah. But later I will do some special selection problem, special cases, not a general. Okay. General. Yeah. So it's in this algorithm. Yeah. All right. Special cases. Yeah. First, for the special cases, and relatively small number. Yeah, because the larger the n number, the harder the problem. So I do not want to give you the n number too large. Okay, so the number n I will give you less than 10. Okay, so single digit n, then it is not too hard to, single digit, yeah, less than 10. Yeah. All right. So then, what do you need to do? Yeah. One commonly given question, you need to find the median. That's one common case, one of the common cases. Yeah. And another one, second largest. Second largest, okay? Yeah. Largest, smallest, yeah, we have simple formula. Yeah. But for second largest, second smallest, yeah, we also have formula, yeah, but you need to do more work. Yeah. So I will talk about that later. Yeah. Largest, second largest. And possibly, go another step forward, third largest. Third largest. Yeah. These two cases, so you will see, yeah, in our questions. Yeah. And usually challenging questions, yeah, because they are challenging questions. Okay, yeah. But before you do those questions, I will give you some examples, yeah, show you how to solve those problems. Yeah. All right. Yeah. All right, so we finished part B. So let me go to part C. Yeah. Before we take a break, so let me talk about the problem in part C in 10-something minutes. All right. So let me get out of the part B. And start a part C. Merge sort. Oh, yeah. Why get to the next slide? Stay in the first slide. All right. Yeah. Part C, merge sort. Yeah. First, let me give you introduction. Why we use merge sort. Right? Yeah. Yeah. All right. The reasons, some reasons about the merge sort. Yeah. Now, when we learn more sorts, we need to know for each sort there are some properties. There are some special properties for each sort. Yeah. So when we apply one of the sorts, we need to use those properties. Yeah. The requirements. What are the requirements of your applications? Yeah. In your real-world applications, you may have restrictions, right? Yeah. Sometimes you have, various restrictions. You need to consider those restrictions. Yeah. So when you choose your sorting algorithms, you need to choose the appropriate one, satisfying, so that sort can provide you the properties that can handle those restrictions of the data. Yeah. All right. Yeah. So let me go to the problem part. Problem number 16, merge two sorted arrays. Yeah. So let us look at a simple problem, basic problem. Before we work on the sort part, let's work on a simple operation first. Just like when we do the insertion sort, we work on the insertion operation first. Now, when we work on the merge sort, so let's study the merge operation. So what's the merge operation? First, I need to describe this merge operation. Merge two ordered arrays. Given two ordered arrays, question, how to merge them to get an overall ordered array? Yeah, that's the merge problem. Okay, yeah. It's a very basic problem. Yeah. And this merge operation, although very simple, so later you will see that the solution is very simple. Yeah. Pretty straightforward. Yeah. But this idea, simple idea, very useful. Yeah. And in many of your homework, final questions, you need to use this operation, this idea. Yeah. Simple, but very useful. Okay. All right. Motivation. Yeah. Why we need to consider this problem. Yeah. Here, as I mentioned at the beginning of this topic, I said there are some special requirements in the real world applications, right? Yeah. So in your real world applications, most of the time you have restrictions, a lot of restrictions. Yeah. So when you do the basic sorting operation, you need to consider various restrictions. Yeah. Here, I use a simple example to describe the restriction, possible restriction you may have, and you need to work around it. All right? Yeah. So what situation? Yeah. Question, how to sort a huge array? Yeah. How huge it is? Yeah. So, yeah. How large you treat it as a huge array? Okay? Yeah. Yeah. So here I want to describe like this. suppose this is the full size of that huge array. Full size. Yeah. How large it is? Larger than you can imagine. Okay? Larger than you can imagine. How large is that? Yeah. Yeah. So let me describe in this way. Yeah. Usually, when you think about a large array, large array, okay, all right. So we consider the size of the data, the size of the data. You need to store your data first, right? Yeah. When you do the sorting, you need to use your computers, right? You need to use your computers. Okay. You need to do the sorting work in your computer. So you need to get your data ready first, right? You need to put your data somewhere in your computer, right? Yeah. So think about that. You need to store the data somewhere in your computer. Okay? All right. So let's imagine. Yeah. So you store the data. Store the data. The data is the array data. Okay? Yeah. Store the array on your hard drive. Hard drive, okay? All right. So at the beginning, before you do the sorting, the data is stored on the hard drive. Yeah. All right. Then you need to load the data, right? Yeah. All right. To do the sorting, you need to load the data into the main memory, right? So there is a, loading step. Load data into the main memory. All right. Main memory. Yeah. All right. Now the restriction. Let me give you the restriction. The data is huge. So big enough, it's a, larger than the main memory. Main memory size. That large. Okay? You cannot load your data completely in your main memory. Only partially. Okay? Only partially. Part of the data. A subarray into the main memory. Right now we know the capacity of our main memory pretty big, right? Yeah. Current computer. Yeah. So current computer. Okay, PC. Here I'm talking about PC. Yeah. So not a supercomputer. Yeah. So usually some people have let's say 32 gigabyte. Yeah. Not hard drive. Here I'm talking about the main memory. Okay. Yeah. And or 64. That's really big. Okay. 32 already pretty good. Yeah. Yeah. 32, 64 gig. Yeah. So that size. But your data size is larger than this main memory size. Okay? Huge. That's my meaning huge here. Okay? Yeah. So you cannot load your data completely into your main memory. Partially, only partially, subarray. Okay. So under this restriction, now I ask you how to sort this array. You need to do it. Okay? You need to do the sorting. So at the end, you need to find a way. You need to solve it technically. Yeah. Because the goal, you need to provide ordered data on the hard drive. Yeah? So your sorting result, you store the sorted array on your hard drive. Okay? Yeah. Hard drive is large enough to hold the data. Yeah. Yeah. The question, how do you solve this problem? Overcoming the technical limitation. That's the question. Okay? All right. Yeah, let me say a few more. Yeah. We use divide and conquer. We use divide and conquer. Although we cannot load the complete array into the main memory, we can load portion of the array. Every time we load a portion of the array, how about that? Right? Yeah? So we divide. We divide our whole data array here into several multiple subarrays. And we make sure each subarray can be loaded into the main memory. Yeah. So that's easy, right? Yeah. Small enough. Okay. We divide our original array into multiple subarrays such that each subarray can be loaded into the main memory. After that, then can we apply our usual, because after you can load each subarray into the main memory, then you can choose appropriate sorting algorithm to sort it, right? Yeah. So then we can apply normal sorting algorithm. But the sorting result is we can make sure each subarray is sorted. That's no problem, right? Yeah. So after we load it, then we sort it, then we export it, right? Yeah. Because after you sort it, you need to write it on your hard drive. Write it on your hard drive. Store it on your hard drive. Temporarily, yeah, because that's the intermediate results. That's not your final results. That's your intermediate results. Okay? Yeah. Yeah. So we have the intermediate results. We have the whole array is still not yet sorted, but the whole array contains a sequence of ordered subarrays. How about that? The whole array. So now, it's not the random data. Yeah. Partially sorted. We can say the whole array is partially sorted. It contains a sequence of ordered data. Now the question, how do you make that sequence of ordered arrays, subarrays, into a one whole ordered array? That question, okay? The answer is, if you can solve this basic merge problem, then how about you merge the first two? Then you merge the next. Then you can merge arbitrary two ordered arrays. Then at the end, you merge all subarrays into the final one ordered array. Then you complete the solution. How about that? Okay, that simple idea. Yeah. Here, that's the the motivation part. Okay, yeah. All right, let's take a break. Yeah. So when you come back at 7, yeah, yeah, probably 7:02, yeah, 7:02. So then we start the second half.